was waiting. Nobody showed up. Just noticed that it was a different class. Okay. Okay, so I guess everyone is here. Most of you are here. Okay, let's start. I think we talk about, I post the, hang on a second. The problems for you, example number 1, number 2, actually. On the more complicated magnetic structure, a 3-legged core. Okay, and dimensions are shown. So here we want to calculate the magnetic flux in each leg of the core, left, center, and right. And in part B, the flux density in each air gap. Okay, and let's do that together. You have some of the solutions shown in the lecture notes, but let's do that in a more details. Give me a second. Let me. I don't have the numbers with me. Give me a second. One moment. Okay, so dimensions are given, and as you can see in the problem, the relative permeability of the core, I didn't put it here, I should. You can, it's already in your post, in the message that I post, but I'm just going to put it here. Mu r is 1,500 times. You can add that on your own in the notes, okay? So we start with the magnetic circuits sketching, okay? And again, the starting point would be to look at the path of the flux, starting with the source, your magnetomotive force, okay? So let's look at that. You already have the final finished magnetic circuit here, but I'll just show you how it works. Okay, I'm not going to post this to just, understand what happens. Okay, you already have the answer. Okay, so your source is where the winding is located, which is in the center leg. So here, this is the center leg of the core, and the center leg contains your core, so you have a reluctance. I'm calling this R sub C for center. It contains the winding, which produces the magnetomotive force, number of turn times the current. Okay, so this is center leg. So in the center leg, it has a magnetic flux of phi center flowing. Okay, so this is what happens. And then when you come to this point, the flux branches out towards the right and the left. The blue and the red. Shown here is phi r for the right, phi l for left. Again, it's passing through the core, so you do the same thing. You go up, go to the right, phi r, go to the left, phi l. And again, now individual path of the flux flows through different materials. On the right path is the core from here up to down here, and the air. So 2 materials. So I'm going to show you 2 reluctances. One for R right, another one for RG2. And then the blue one completes at the bottom here, which is the one that we have. Okay. Similarly, on the left, which is the red flux, VL, two materials again. This is G1. So very similar to the right. Two materials, two reluctances, and it completes the path. Phi left. This is phi C. So this is R right, R left, sorry. RG1, which is what we have here, right? So again, you look at that. Now this is the important part. Once you got the circuit right, that's the starting step. Now, important part is to look at how you find the reluctances for each path. We start from the center first. And we remember the reluctance equation, length over mu A. Okay, this is how I memorize it. That depends on how you are comfortable with. So this is the length of that path of the flux, the cross-sectional area of that path, and the materials of that path. So this belongs to individual flux path. So in the center, in the black path here, it flows into the center leg. Okay, so you must measure only this length, top to the bottom. That's it. That's what phi C is. So that path is the dimensions shown here in the notes. Half of the bottom, 7.5 plus 30 plus 7.5 in centimeter. Okay. So that's the length, LC in the center length. AC, the center cross-sectional area. You know the dimension here, which is 7. The depth is 5, so 7 times 5, all in centimeters. Okay, so that's what you have. So to express RC in more details, this is what you're going to get. RC is going to be here, you get that, 7.5 plus 7.5 is 7, so it's 37. So it becomes 0.37 meter. Don't forget to convert to meter. And you cannot get that wrong. You must know how to do that in centimeters to meter. Divided by mu C is the core, so this is mu R, which is 1,500 times mu naught. AC is 7 times 5 is 35 centimeters times 10 to the 4th to meter square. So this is my RC. You can calculate this, okay? So your job is to find out what is that value, okay? So that's the center leg. Now, repeat for the right path. The right path starting from the top of the core. Can you see that? Let me know if I'm off screen again. It flows from this path down here towards the left. That's it. Only half of the path. So this is the length. So what is that length? Again, it's a center of 7, so 7.5 plus 30, another 7.5, 7.5, 3.5, that's 1. Same thing here, it's symmetrical, 7.5, 30, 7.5. Same thing, 7.5, 30, 7.5. So it's 3 times 7 divided by 2 plus 30 plus 7 divided by 2, 3 times that. That's why I put it here. So in this case, your R right becomes 3 times 0.37 centimeters. Divided by, again, same thing, 1,500 mu naught. Cross-sectional area, this is 7, depth is 5. This is 7, depth is 5, so same cross-sectional area. 35 times 10 to the 4th meter, this is meter, sorry, square. Again, your job is to find that out, okay? And now, notice that this is not the exact value. We kind of like omit the distance of the air gap to make it more precise. You can minus that, but that's not needed. Why? because this is very small, only 0.05 centimeters. So if you do that, it's not going to affect the values as much. So you can neglect that. Okay. The reason we can do this, notice that what we're saying is that L on the right path is approximately equals to 3 times 0.37 meter. Okay. If I don't want to approximate that, is actually to do 3 times 0.37 minus what is P2? 0.05 centimeter, 0.05 times 10 to the negative half meter. So you notice that that is a very small number. Okay, 3 zeros after the decimal point. So you minus that, it's almost the same. So we can neglect that. Okay, so you don't need this. Okay, the reason that we can do this is that we assume that LR is a lot larger than G2, which is the case, many times larger. Okay, so this is an approximation, but a very close approximation. Okay, and again, we do the same thing for our G2. Our G2, the flux passing through air up gap 2, which is 0.05 centimeter. This time it's air, so it's mu naught, no R. And AG2, now this is, you have to be careful of this because the area in the air gap, I forgot to check, you can hear me, right?
Yes,
okay.
I'm listening here.
Okay, thank you. So it's AG2. Now, notice that in this problem only, the problem states that fringing effect is not neglected. Okay. Fringing effects are, because there are 2 air gaps, are not neglected. Okay. Remember fringing effect. Remember that we talked about that last time, is when the flux passes through the area. 2-dimensional drawing. So this is your path of the flux. The flux goes to the edges, the fringe. This edges here increases the cross-sectional area of the air gap. See, the distance would be wider compared to that of the core. So you do this, I can draw a 3-dimensional, I guess. This is the core. So that's area of the core, right? The blue ink. The area of the air gap would be this plane here. I'm not sure I can do that. Like that. Larger. See? Larger. The red. This is AG. This problem says AG is 5% large. Is it 5? Yeah, 5% larger. So it must equals to 1.05 AC. And your AC, you know that is 7 centimeters times 5 centimeters, just like the one that we calculate. So that's why there's 1.05. This is due to fringing effect. See, that's why your RG2, oh, put that there. I missed that in the note. You need 2 here. G2 divided by mu naught AG2. AG2 is the same as AG1, which is 1.05 times AC. We know AC from the first calculation of the center leg. You know G2, you know mu naught, you know AG2. So in this case, you can put RG2 equals to 0.05 times 10 to the minus 2 in meter divided by mu naught, and then 1.05 times 0.05 times 35 times 10 to the 4th meter square. So this is our G2. Again, do your own calculations. So this is the right leg. Repeat the same process for our left. If you notice that the left is symmetrical to the right in this, for this core, right? This is symmetrical. 737, again, 730, so it's the same. So we can say that R left would be the same as R right. You don't have to recalculate. RG2, you just change the values of the gap. The rest is the same. In this case, it's 0.07. So that's how you get all the reluctances, 5 of them. So if this is now you have the circuit, you have the values. You have to change this into a more equivalent circuit that you can calculate. Okay, and you have to note one thing. The center leg flux, phi C, branches out to 2 paths, R and L. So phi C is like a current, equals to phi L plus phi R. You have to keep that in mind. And then you redraw this. It turns out that this is the equivalent circuit of that. RC plus the parallel branch of these left and right, shown here. Again, you turn that into an equivalent circuit. The final equivalent circuit is this, where this is your magnetomotive force, center flux, phi C, and Req. What is Req? Req is the parallel of these two branches in series with RC. Okay, I'm showing you in here. RC plus the left branch, RL plus RG1 in parallel with the right branch, RR plus RG2. You cannot read, that's RG2. Okay, and the parallel calculation for this, you know that, or you should know that already, is the product divided by the sum of the two parallel branches. So this is the product of the left and right divided by the sum of the left and the right. And then you add that to RC. Don't forget to add that back to RC. So my Req is RC plus this product. If you do this right, now this is the part that you got to do on your own. Okay, please do that. So that way, if you didn't get the right answer, you can ask me in class next time. If you do it right, your Req should be approximately 204 kiloampere per Weber. Do it right. So do that, please, on your own. Like your self-study. Remember, this would be a midterm exam. Okay. Now, go back to the equivalent circuit that we have based on that. So we know that based on magnetic Ohm's law. Okay. Magnetic force. Magnetic circuit, Ohm's law gives you magnetic force, which is N times I equals to phi times Req. In this case, phi C, because this is our flux. So now you can calculate the flux inner center leg. Phi C would becomes Ni divided by Req, shown in the notes here. You know N, 300 turns. You know the current, 1 amp. You know Req from the calculations of each reluctance. Should be approximately 204, give or take, kiloampere turn per Weber. If you do that right, you're going to get the flux in the center leg, which is 1.47 milliweber, 10 to the negative third Weber. So that's the first part of the answer. Then we got to calculate the other two paths, left and right. Now we have this phi C, and we know the relationship between left and right, which is phi C is the sum of these two. So you can use what we call the flux divider in a magnetic circuit, similar to a current divider. Okay, remember the current divider in your circuit 1? Okay, you treat a flux like a current. So that means based on this magnetic circuit, the product of your phi L times these two must equals to phi R times these two added together, shown here. The left flux times RL plus RG1 must equals to the right path times RR plus RG2. So this is equation, you have two unknowns, which is phi L and phi R. You need another equation, which is phi R is phi C minus phi L. You have two equations, you solve you should get phi L and phi R, these numbers. If you add them together, they would have that 1.47 milliweber. You see how that works? That's why we make use of the magnetic circuit, imitate the equivalent circuit, because the flux would be acting like a current in a regular circuit. And the voltage, the magnetomotive force on each branch would be like a voltage on the circuit, on the electric circuit. See, that's how we can do that. So now we have the answer for part A. Center, left, and right. These are the numbers. Again, I suggest you go home and do your own calculation if you get these numbers or not. Like a practice problem. Actually grab a calculator and calculate individual one. The most important part is, well, every part is important, but these the calculation that I told you to do. These are simple, right? You just grab a calculator and calculate that. The important part is to find out REQ. You cannot make that, you cannot get that wrong, because if you got this wrong, the rest will be wrong. Okay, you got to double check on these numbers, make sure that it makes sense. Okay, once you got that, then the rest is pretty simple. You can then use that to find out the flux path. Okay. Okay, so now part B, flux density in each air gap. Okay, flux density in each air gap. Remember, we know that gap 1 is on the left leg. So BG1, air gap on the left, I give you VL here, must equals to phi left, the left flux divided by AG, put that in there please, AG1, I think, left is 1. And this is G2. Turns out that AG1 and AG2 is the same. If you understand this, this is 1.05 AC. Okay, you can do that on your own. Okay, you know flux in each leg, phi left and phi right for gap 1 and gap 2. You know AG1 already, which is the same thing as AG2, which is 1.05 times the core cross-sectional area. So you calculate that. Okay, so that's part B answers. Okay, so this is the magnetic circuit. There are a few end of chapter problems you can practice, so you should do that on your own. A few non-symmetrical chord you can try, so please do that. So understand what we're doing. If we have time in the chapters, we'll do a few more examples on this. Okay, but now let's go to our next topic. Okay, so today your homework, you don't have to submit, is to do all this stuff. Check my numbers. Okay, you should get these values. Okay, if you don't, you know, double check on your answer. And still you can't get these, let me know. You can ask me, did I do wrong or I am wrong? I can be wrong. Okay, all right. Now, so far we talked about this magnetic field, which needs magnetic circuit. I'm sorry, which needs a ferromagnetic core. So what is so special about ferromagnetic? Okay, there's only one. It's a family of steel or iron metal, but notice that these are the only type that you can make them into a permanent magnet. You never see permanent magnet made of, you know, gold or copper or zinc. Okay, there's a reason for that. So we're going to look at magnetic behavior of ferromagnetic materials. Okay, remember the reason we choose this is they give you it's a high mu metal. High mu lower the reluctances, gives you a better flow of the magnetic flux, stronger magnetic field. That is the reason. Okay, and we found out this equation earlier that your magnetic field or flux density B depends on this mu, which is the property of the core material. and the effort of producing that, H. Remember, same effort, but different property of material, you get a different B. We like B, we don't care about H, okay? Mu R, relative permeability of ferromagnetic material, the iron family, is relatively very high compared to other non-ferromagnetic, which is about the same as free space, your mu naught, okay? About 2,000 to 6,000 times. There's even higher numbers now. You can actually make a compound, a ceramic component type, what we call this a high mu metal. You can do that, you know, manipulate the materials a little bit to achieve even a better mu, okay? But you have to know the reason higher mu gives you lower reluctances. Why are they so special? Because it turns out that ferromagnetic materials contain what we call is magnetic domains. So if you kind of like have special eyes that you can zoom in on the structures, kind of like the molecule size of the metal. I'm drawing a crude drawing to give you an idea. These are not the actual thing. Magnetic domains. Think of it like a tiny magnets. And these domains are randomly oriented in the materials. So you kind of like you get a piece of iron. If you take that piece of iron, it's neutral. It's a regular iron, it's not a magnet. Why is that? Because these domains are randomly oriented, meaning that one moment my magnetic field might go that way. This atoms might contain nothing. This atom might contain a magnetic field goes downward with the rev, you know, like that, randomly. See, I'm just gonna draw a few, kind of like that. And then what happens is that all these cancel each other, give you zero magnetic field. See, we call that term unmagnetized. It is not a magnet. It doesn't have any magnetic field. That's pure iron. Well, not pure, I'm sorry. That's when you dug it off the earth and you don't put it, you know, energize it or do anything with it. Just a regular iron, like a piece of nail or your regular paper clips. Okay, if your paper clip is made of, you know, iron family. Now, you can turn this ferromagnetic into, magnetize it into a magnet. So what's so good about this is that when external energy can be anything, okay? Most of the time it's the magnetic field or a current, okay? So when external energy is applied to these domains, they will orient themselves, okay? Let's assume I have this one, okay? Now if I apply external field, let's say a current, well, let's say a magnetic field, another magnet attracts to that. If my magnet flows this way, my magnetic field be external, okay? And assume I can control this. I start from another strong magnet, a weak magnetic field, okay? What's going to happen is that they will try to turn, okay? How do we know this happens? Because we can observe. This is the experiment that we did, okay? We have the magnetic behavior in a ferromagnetic material observed by set up a core, the square donut that we discussed earlier, okay? With a variable current, assume it's DC, wrap around, injected in a coil in one side of the core, like in this example here, and assume this is a variable. You can increase it from 0 to a certain numbers, okay? And then we measure phi in our core. There are meters that you can actually do that, okay? How do we know what happens? We plot between phi and I as a function of the current. We know that we apply stronger current, phi will be stronger, okay? Let's see how that works. So this is what the resulting plot is going to be. It's a plot between actually the magnetomotive force, which is the number of turns times the current value, amperes turn, versus the flux. We call this curve the magnetization curve. As you can guess, when there's no current, you have no flux. When I increase the current, let's say 10%, my phi goes up 10%. 20, it goes up to 20 until I reach a certain number. Okay, now notice that from this point out up to right about there, like before the curve starts to bend or to flatten out, this is a linear region I wrote here, the linear region of your magnetization curve. Okay, then when you increase more current, remember the number of turns cannot be changed. You will only change the current, the variable current that we injected into the coil. You inject higher current now. Now what happened is that your phi starts to what we call saturated. It doesn't go up as what we wanted. It starts to flatten out. Okay. Inject even more current. Your phi goes up a little bit. Now even higher now. It starts to stay flat, no more increasing. If we do this for a longer period of time, it will be just like constant. We call this saturation region. Okay. Now we can also map this curve. Okay, we know that B is equal to phi over A. See? So we know that B is proportional to phi. Assume constant area. Similarly, we also know that H is Ni divided by L, right? This is your magnetomotive force divided by length. So we also know that H is proportional to the magnetomotive force, assume constant length of the core. So if they are proportional, we can map this magnetization curve to what we call is a B versus H curve. Okay, because they are these linearly proportional to phi, shown here. H is linearly proportional to length. You get the same shape, linear region, saturated region. This is called the BH curve. The slope of the BH curve, you look carefully, is delta B divided by delta H, or B over H, which is permeability that we studied earlier. See, so the slope of the BH curve is permeability of the materials of the core. Notice that it is not actually linear. It only linears in this linear region, but when you change into the saturated region, your mu value is going to change. That's why you recall in the assumptions when using the magnetic circuit, we assume linear or constant mu. Mu is constant only in the linear region of the BH curve. See, when you go into a saturated region, your mu starts to change as you increase it in higher H. Okay. Now the point is, why the saturations occur? you would assume that I inject more current, it's going to go up, up, up in a linear manner. That is not the case for your ferromagnetic. Okay. So explain to you before that the slope, the BH curve is permeability. Okay, that's done. Okay, now why does ferromagnetic material saturate? Why don't I get more flux if I increase more flux? Okay, let's assume this is linear. If I step 50%, I get 50% phi. Another 10, I get 10. If I step another 20%, I should get the same. I don't get that. Why? Why does saturation happen? Okay, so when low external magnetic field, let's say low current, is applied, only a few domains will try to orient themselves. Like the example that I draw earlier. I have an external strength field here, low current. Only the one that's kind of like going towards the right would change. So like this guy, he's gonna go that way. This guy, no, he's gonna stay. That's gonna stay, 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 stay. Let's do another one here. Okay, so that one's gonna go, stay, 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 stay. Everything except this guy. This one's gonna change. This one is already on the same directions that it is. So maybe in this case only 2. Okay. I increase even higher strength. Now, this guy would probably change. Okay. This guy is going to change. Okay. And that's going to happen as long as you go into higher and higher. But now the point is, in the beginning, at low current and low field, you have lots of flux or domains that can change, right? So now you can do that in a linear manner. Okay. Close to saturation. Let's say now I increase it even further. This one's gonna go. Okay. This one's gonna go. This one's gonna go. This one's gonna go. Okay. This one's gonna go. Right, very high now. I'm close to saturation. Now notice that if I do it even further, increase it even more, like very, very high external field, very high current. Notice that now I don't have many domains left. It's only like this guy here, that one, that's it. I assume that one's already gone. So I have only 3 left. So I don't get linear relationship anymore. I increase this 10%. There's only 3 now, 3% left. So only 3 will try to change. And then when I do this even more, assume this guy's already changed. All the domains is changed already, right? I apply even more current, even higher field. I get no increase in phi anymore because all my domains already changed. This is the reason why saturations occur. Okay. So you see how that works? So so low current, the domain, only some will orient itself at a medium value, many more move. Okay. As the external field is very strong, not very many more are left now because most of them is already turned. So there's only a few that can turn. So only a few left will orient themselves. This is the cause of saturation effect. See, everybody's already turned, so you get nothing more even if you increase even high current. Okay. Now, so that's for assume a DC. So we know how we achieve this saturation curve and BH curve together. Sometimes they use synonymously. There's a factor of linear. Okay, now what happens if we change this current into an AC world, sinusoidal? Turns out it leads to what we call is energy losses in ferromagnetic core. Okay, what does that mean? It means that if there is an AC current applied to the winding instead of DC, again, a variable now, assume sinusoidal, like this one in the red curve. Okay, if we do that, this time my current is AC, again, variable AC source, sinusoidal, like I drawn here. Okay, I start from point A, increase the current to point B. Okay, my magnetization curve, because this time it's negative current also, I got to show this in 4 quadrant. Here on this positive X is positive current, on the left side is negative current. Okay, now let's see what happens. So I go from A increasing to B, my current go up, right? I get from A going up, very high current starts to saturate. So at B, everything's already turned, every domain. So that's peak. Now I gradually decrease the current. Actually, sinusoidal, it's going to decrease by the signal itself. B down to C. So your current magnitude comes down. Turns out that your flux, you think that, hey, it goes from A to B. If you go from B to C, it's supposed to go that way, the same path. Turns out that it's not like that. It goes to a different path. So B to C goes like this, B down to C. See? So magnetic domains are like, are like people. You can think of it like this. So some is easy to turn, right? Some is stubborn to turn. Reverse action happens. If you decrease this field, some that's very stubborn won't try to turn back to itself, to its original position. It likes where it is, like stubborn people do. Some people are very, easy to listen to, different ideas. Some people are stubborn. Think of domains like people. Okay, a variety of them. Same thing here. So when you decrease the current, your external field is weakened. You would think that it's going to go back to the same path. It does not. Stubborn domain remains at its place while the easy one go back. So that's why when you actually reduce your current to 0, which is point C, you have what we call is a flux left inside your core. We call this phi subscript RES, stand for residual flux. Okay, so meaning if I have a piece of iron, I zap some external current into that and then take the current off, my iron becomes magnetized. Notice this from this path A to B back to C, 0 current again. But now your phi is different. Initial condition is 0, now it's non-zero, residual flux. This is the method this is the principle that we use to make permanent magnet in the industry. Okay, you can go to YouTube and search for how magnets are made. It's a documentary in the Discovery Channel. You can do that. One of the ways that they do, if I recall, they have like a tube of iron, like that, like a donut shape, like a cylindrical tube. Okay, and then they separate this into like a kind of like a donut, sort of like a ring, a thick ring. Okay, and then they put this rod. It's going to form into a big rod, right? A long rod. Sorry, a long tube. And then you put this tube. I'm sorry, you put a copper rod through this tube. This is copper, a conductor. Okay, then you zap a current to that conductor. Connect this to a source, maybe a switch. So the current is going to pass through this high current. So you put a field in there. So this randomly oriented domain would flow that way. Then you disconnect the switch. And this is how it's done. When you put the current into there, it's going to go up very fast, back down. So you have residual flux in there. Then this regular ring of iron becomes a magnet. See? Or you can do it at home using a paper clips. Go to your refrigerator, wrap it to the door of the refrigerator. Maybe it made a few times. That paper clips become magnetized. And that's what you are doing. You apply external field from the permanent magnet from the refrigerator door to your paper clips. When you get it off from the fridge door, it's going to leave some residual flux in the paper clips. Okay, now back to our lecture. Now we're back to point C now. The current now becomes the negative territory now, sinusoidal. C to D, you decreasing the magnitude in a negative manner, right? Here at 0 amp, now it's going to be negative some number, let's say negative 10 amps at a peak value. So what's going to happen is that now your flux would reverse direction here, and then it's going to try linear, and then saturates at D at the peak. And again, same thing from D to E, just repeat process. Less negative, but you decreasing the magnitude from -10 down to 0. So your flux would go down. And again, reach at peak E, negative residual flux. If you follow this again to a new cycle, E now is going to go to B. And then back down to C, D, E. It will form a loop. It will never come back to point A again. Okay. So this is what we call is hysteresis loop. Okay. Okay. So now what I wrote, so this is how the BH curve of all 4 quadrants is formed. And this loop, the red loop that we see, we call this hysteresis loop. Okay. Now note the flux traces out a different path from the ones it follows. See, when it goes that way, when you try to change the current, decrease it, it doesn't go back to the same path. We form a new path, like a loop. Okay, never trace back to the previous path. Okay, so it follows when the current increases. This behavior, the textbook says use these words. If you understand, that's okay. It's kind of like difficult to grasp a little bit for non-English. Okay, these dependence on preceding flux history and resulting in failure to retrace. So the key word is to retrace its previous flux path. Notice that it would go back to the previous moment. It will follow a new path. This is called hysteresis. This phenomenon is called hysteresis. The path B, C, D, E forms a loop called hysteresis loop. Okay, this loop is not, it's good. Okay, on the one hand, it's good because this is how we make permanent magnet. Remember that? You want residual flux in there being left without any current, a neutral current. So that's a good thing. But there's also a downside to that because this loop causes energy losses in ferromagnetic core. Okay, and it turns out that we want to cover this. These are more like materials engineering, but it turns out that these energy losses is proportional to the area of the loop. Okay, these energy losses is part of the core, what we call is the core losses. So this means that if I have 2 different iron, different from a different country, let's say, one has this hysteresis loop shape. Another one has this shape. Okay, assume the same price. I would choose this one because my core loss it will be smaller because I have a small area compared to the red one. See, this is what we call is inevitable effect. You can't get rid of these losses. You can minimize it, but you can never get rid of it. It's part of the deal, kind of. Now, you know, we learned that, hey, ferromagnetic is good because they have this domain that's going to give you the, you know, the magnetization effect. Okay, so that's the good part. They also have some downsides, some drawbacks. One of them is these core losses, these hysteresis losses. Okay. Turns out that there's another losses. Okay. There are two types of core losses. One is hysteresis losses that we just discussed. Another type of core losses, which is called eddy current losses. Okay, is caused by the eddy current due to the flux. Okay, what is eddy current? Eddy current is, you know, eddy. It's like a looping thing when you kind of like throw stone into the water, kind of like a ripple effect. So this is called eddy. Okay, so when your core, I'm showing you here a block of core, a cube of core, has a magnetic field coming out or magnetic flux coming out. Okay, using your right hand rule, B is coming out. If you look at the top view of this is like that. The black dot is the point of the arrow of your magnetic field B. If you do that, it's like that. Your finger's gonna show you the directions of the eddy current. See, it's gonna loop a looping current. This is what we call eddy current. These currents produce I square R losses in the core. Okay, remember, if you have a current, you always get I square R losses because your core has a resistance, ion resistance. So it's not actually a very low resistance actually. What is the resistance? It's in the form of rho L over A. Remember that, conductivity, length divided by the area. Okay, so that's where the materials, the rho or the resistivity of each material is different. Copper is better, silver is better, iron is not really good, but it's better than, you know, non-metal. Like wood is pretty bad. Plastic rho is very high, sort of. Okay, so these current would generate these I square R losses. Now, for this type of core losses, we can minimize it. Okay, how do we do that? Before I do that, so I concluded here, core losses is what we call P core, sometimes called PH plus E, like that, is the hysteresis losses, P sub H plus P sub E, eddy current losses. So you can write P core in two different, in your textbooks, probably two different notation. It's either P sub core or P sub H plus E. So it's two types, hysteresis, eddy current. Now back to eddy current a little bit. If you notice that your electrical machine inside, not the casing, so the one that you see in the lab is the casing of the machine. The one that has windings contained, like the transformer, everything like that. Your core, like also the one in your example, if it's a properly designed core, this core will never be made of a solid iron, a chunk of iron. Okay, so meaning if I have a core, let's use a simple one, the square donut core. In real life, your core is going to be made of lamination, thin sheets of iron stacked together, right? You get the idea? There's a reason for that. So you never see a piece of iron like this, a solid piece of iron that thick. It will never work because the losses in this core would be very, very high. So it's going to generate a lot of heat, a lot of core losses. That's not going to be able to produce any useful, machine. So this is incorrect design. This is the right design. So these are pretty simple to make now. And one more thing, individual sheet. So how do you form this core? Actually, you have a metal iron sheet. Let's say like this paper. This is maybe too thin, like probably a millimeter or less thick, half a millimeter thick. And then you coat it with enamel or some varnish, magnetic insulation type liquid. You dip it. So if you form this sheet, and then once you have that sheet, you can make it into any shape. You stamp it using a stamping machine, sorry. Maybe forming like a disc. And then you stack that disc to form a cylindrical shape. Okay, so that's how you make a core of electrical machine. Never made of a chunk of metal. You don't see a core that's like this cylindrical shape, like that. Doesn't work. Why? One of the points of lamination is to reduce your eddy current. So your eddy current, remember, is the I square R losses, and your resistance depends on the length, the path of the current, and the area of the current. So assume I have two pieces of core on like this, only the top view of the core. Another one is like this, okay? But the second one, I break this into, let's say, 4 parts using lamination. This one is a whole chunk of iron. So if my magnetic field is coming out here, my path is going to be pretty long. See? The whole path. Here, my path is going to be very short. This will reduce my resistance in the core, hence reduce this core eddy current losses. See? So that's how lamination worked. That's why, like I said again, you will never see electrical machine made from a bulk iron casing. The outside that you see are the casing, so that's not part of the machine. Well, it's part of the machine, but it's not the one that produces the magnetic flux. Okay, if you open it up, all the core, you can image search. You see lamination cores. Even your textbook has a picture of that. It always made of lamination, steel or iron. These are the reason to reduce the core losses. Okay, so now we know, hey, ferromagnetics got a good point. The benefit is, high mu values, less reluctances. The disadvantage is these inevitable losses we cannot avoid: hysteresis loop and eddy current. Okay. But again, the benefits outweighs the gain. I'm sorry, the benefits outweighs the risk, the losses. So that's why we are using ferromagnetic as our main materials for, motors and generators today. Okay. So this is the basic why ferromagnetic is important and the behavior of it. Okay. Okay, next is Faraday's law. Okay. This relates to your, so we use this first because it relates to your magnetic field and magnetic flux. Faraday, some say, is like the father of electricity. I Googled the other day, there are many guys. There's a Voltaire, what's his name? I forgot. The units of the voltage. He's like, I think he's French. He's the first guy who discovered that there's a voltage potential in a I forgot, like a salt and a metal. I think he stacked it up, and he's kind of like the first person, the first persons, I think there are many persons, invented battery, kind of like that's you can Google that. He's also one of the founder, considered one of the founders in electrical power. Faraday's another guy too. I think if I remember correctly, Faraday discovered like static electricity. I think maybe you can check that out. I forgot already. Okay, but anyhow, our important point here is he found this law. Okay, we call that Faraday's law. What the law states in a short manner here says that induced voltage from a time changing, meaning AC, magnetic field and what am I writing here? I did write this pretty good. Hang on a second. I get confused with my own handwriting. Induced voltage from time changing magnetic field. This is the equation. EIND equals to, so this is the law, minus dphi by dt. Okay, so if you recall, go back to the fourth principle that we discussed last week, the fourth one. Refresh your memory here. I have a time changing magnetic field. Okay, I have a coil inside that, not moving. This is AC. I get induced voltage in this coil. And this is this is Faraday's law. So this is AC, a simple seg, sinusoidal. You have a core stationary. You put it through the time-changing magnetic field or magnetic flux here. You measure that coil, it has a voltage. And this is the relationship. Now, the original law has a negative value in it. So here, EIND is induced voltage in the turn of the coil, one turn. Phi is the magnetic flux passing through that turn. Okay, if one turns like this, if you have n turns, you just multiply it by n. The expression with a negative sign indicates that if my flux increasing with time, I get a negative voltage, opposite action. If my flux decreases with time, I get a positive voltage. But we will neglect that negative sign in this course only, just to get rid of the confusion. We don't care about changing in the positive or negative directions, okay? So here, this is the negative sign is the expression of Lenz's law, another scientist. And he's mainly famous for magnetic levitation. You can check that out if you want, you know. Anyway, so this is the equation for n turns of coil. Okay, we will omit that for our class, only for this class. Okay, I clarify in the next slide, in the next lecture notes. The negative sign is omitted in this course. Then what you have left is just induced voltage is n dphi by dt. This law is the basis of transformer reaction. Okay, so no movement, but you need time changing, which is AC. That's why transformers only apply in an AC voltage system. There's no DC transformer. Okay. The total voltage induced in a coil of n turns, now if we have more than one turns, is induced voltage is the summations of each turn from I equals to 1 to n of each individual voltage. So E sub I is induced voltage in each individual turn, which equals to d phi I by dt. I remember, if this is your core, this is my coil. I'm drawing only 4 here. So this would be phi1, phi2, phi3, phi4. Notice that the flux in each path would not be the same. The edges, winding, turns are weaker, right? No neighbor on the top or no neighbor on the bottom. 2 and 3 are sandwiched, so they have stronger phi. Okay, so that's why I wrote. That's why the equation is shown here: d phi I by dt. Okay, and it's the sum of these. Okay, substitute that back into the summation, becomes d phi I by dt. Take the derivative out, so it becomes the derivative of e n I equals to 1 to n phi I. Okay, we call this bracket flux linkage, the linking or the linkage of all the fluxes, that parameters lambda. So substitute lambda back, becomes d lambda by dt. Okay, so this is just to show you what happens. Okay, we'll come back to that later. So now there's a term, don't get confused. There are the term leakage, leakage. And there's this one that we talk about, this linkage. Linking. So here, if you look at that, there are linkings of flux. See? So these are linking. This is called lambda. Okay. Leakage flux is this one that go out. Okay, don't get confused about the wording. Okay. So this is what Faraday's law states. Okay. So that's the basis of transfer reaction. We will go into details. This is just to introduce you. Hey, transform reaction come from the concept of Faraday's law. Okay. Next is the Mohr basis of Mohr reaction, which states that production of induced force on a current carrying conductor. Okay, so I believe this is the third principle. We didn't order this according to the principle that we talked about last week. Okay, but remember, in the principle that we talked about last week, the first one is you have a current carrying wire, has a magnetic field. The second one is a generator's action. You move a conductor in a magnetic field, you get a voltage. The third one is the Mohr basis of Mohr reaction, where you apply the current in the conductor in a magnetic field. You have a force on that conductor. And then the fourth one is the time changing magnetic field that we discussed. Okay, so this is the third principle, meaning you have a current carrying conductor. The input, you get induced force. Okay, so it says here, current carrying conductor inside a magnetic field, resulting in induced force will be present on that conductor. So this is the basis of Mohr reaction. And the related equation is, you've seen this in physics already. Vector F, which is induced force, is I times vector L cross vector B, where I is the magnitude of the current, vector L is the length vector of the conductor inside your magnetic field. And it has the same direction as the current, points in the same direction as the current. Now, why it has to be like that? If my magnetic field is like this, let's say I have a magnetic field here, north and south. This is my magnetic field, but my conductor is longer. So this is vector L only. Assume the current goes this way. So this is the directions of vector L, only this point, inside the magnetic field. What's outside doesn't count. See? And it has to be the same directions of the current. B is the magnetic field. And then this is the vector equation, turn them to scalars ILB sine theta, where theta is the angle between vector L and vector B. Okay. And you have to use your right hand rule. For this class, it's going to be kind of like a different, maybe in general, for the right hand rule. Okay. This right hand rule applies to the cross vector also. Okay. I forgot to post. I used to have a picture, I think. I'll try to post that later. It's difficult to do here on live feed, but here, the starting point is to have your right hand. I'm assuming everyone here has a right hand. Okay. You form a corner of a cube or a box. Meaning what? Index and middle is 90 degrees. Index and thumb, 90 degrees. Thumb and middle, can you see that? 90 degrees. Three-dimensional world, all 90, a corner of a cube. Okay, now, somebody post something? Hang on. If you ask now, sometimes I can't see the post. Okay, nothing here. Give me a second. Why is it not going back? Come on. Okay. Hey, hang on. Am I back yet? Okay. You can see my hands, right? Okay.
Yes.
Now, start with, this is the sequence. Don't forget the sequence. The sequence matters. Index first, middle later, result is your thumb. So index, middle, thumb is the result. Showing you here in the lecture. Index point to the directions of L, which is the same as the current. The middle finger points to B direction, magnetic field. Your thumb is the resolved vector F. Okay. This is the same as the cross product of two vectors. Remember, the cross product of two vectors will give you a vector quantity. So I'm showing you in the box here, A cross B, index is vector A, middle finger is vector B, the result is your thumb. So same thing, because you're having L cross B. So this is a kind of like two vector crossing together, first crossing with the second. So first is index, second vector is middle. This is the result. Okay, let's try this example. You have to practice this. Again, in exam, almost every semester. So I'm showing you here the magnetic field in the red ink going into your page or my page, the bottom of the arrow into page in here. I have a conductor in the blue ink, a tube here where the current is flowing down. So you know my vector L is flowing down. We know the length inside the vector B. We want to know which way is the force. Okay. So you start with index L. Give me a second. I can't do this. I don't have space. You have to follow this carefully. Okay, let me get my iPad stand. Oh, we don't got time. Let me finish this part so that way. Okay, I'm back. Sorry about that. So let me finish this part. Let me. Okay. Can you see my hand, right? Where? Hang on a second. Okay. Now, give me a second. Okay. Okay, you see my hand, right? It's difficult for me here.
Yes, sir.
Okay. So the current goes down, starting with index, going down, right? You form a corner of a box. See my index finger now. Now, you keep this, you don't change the index finger. It is always down. Then you rotate your middle finger to the direction of the magnetic field. In your case, it's into the page, right? So in this case, I'm gonna do it like this. I have a difficult time doing it. Okay. So you spin your hand, see, down into the page, you see? So in this case, I'm pointing to the front of my home. My thumb's gonna go to the right. Let me try this again. Yeah, that's better. Hang on. Let me hold my iPad. So down, okay. Spin. See my index, my middle finger goes towards the table. Your thumb goes to the right. That's how you get induced force. Okay. You see what we're doing. So first, a lot of the problem mistakes that I found in the past is that you don't keep your index the same direction from starting. Some of you is going to say, hey, down. Then you say, hey, let's do that. B. No, that has to go back. See, like that. Okay. So practice this with different kind of like, orientation of your vectors. Some will not give you a force. Okay. Okay. It's already, oh, it's out of time already. Hang on, let me see if I have an example. I guess we can try this. Let me give you a fresh example. Hang on a second. Okay, just one more. Okay, let's say I have my, let's see, magnetic field, like that, upward. Okay, my red is my conductor. Let me know if you cannot see. You can see, right? Okay, now the current goes towards the right. We want to know if there's a force on this or not, and which direction. So you start with your index, which is the current, go towards the right. See? Okay, you see my index, right? Then B, so that doesn't change. Then my B is the middle. Your thumb points upward. So this problem, my force is upward, out of page. So my force is out of page. See? So you can see the tips of the arrow. Okay? So you have to practice this first, make sure that it's 90 degrees each. And then when you start with the index, once you go into the middle, don't change it. Don't say I, then you say B, like that. Don't try to change that. The result is always your thumb. Okay? Any questions now? All right, then I'll stop here for today. I'll see you again on Thursday. Okay, and if we have time, we'll do a few more examples on this. It's going to be also applied to the induced voltage also. All right, see you on Thursday. Bye.
Thank you, Ajahn.
Thank you, sir.
Thank you, sir.